In today's class and video, we are going to look at how to plot a BSA calibration curve using the Folin Lowry Assay. So first of all, what we have to note is that in every enzyme assay, the protein concentration of the enzyme preparation must be known. And also, it is important to construct a calibration curve each time there is a need to measure protein concentration of a sample. So basically, in this mini project, protein concentrations will be determined by the Folin Lowry method, and to do so, a calibration curve will be constructed using a standard protein, which is BSA. So now let's look at the activity involved in plotting a calibration curve using 1% BSA. So we are going to use the 1% BSA as our stock to prepare the various concentrations that we want to use for the calibration curve. So materials needed, so we have pipette, micro pipette, of sizes. So we have the 200 microliters, 100 microliters, and 10 microliters. So we also have the Folin reagent, which is being diluted in 1:10 and needs to be freshly prepared. So we also have the 1% BSA, which is equivalent to 10 milligrams per ml, and the BSA also needs to be freshly prepared. So we have the spectrophotometer set to a wavelength of 750 nanometer, and we have the alkaline reagent. So now let us look at the solution or reagent preparation. So we'll start by looking at how to prepare the 1% BSA. And don't forget, initially I said the 1% BSA is the same as 10 milligrams per ml. So now let's see. So for the 1% BSA, so what it means is that we weigh 1 grams of the BSA and dissolve it in 100 ml of distilled water. Now, if you want to convert the 1% to milligrams per ml, now so we know that the 1% is 1 gram in 100 ml, so we will convert the grams to milligrams. So and we know that 1000 milligrams is equal to 1 gram. So what this means is that the 1 gram over here, we will multiply through by 1000, and it will become 1000 milligrams per 100 ml. So if you should divide, so this 100 will cancel this 1000, so you will get 10 milligrams per ml. So we can decide to prepare the 1% in 50 ml. So to do this, we weigh 0.5 grams of the BSA and dissolve in 50 ml of the distilled water. So some key note. So what we have to note is that we have to prepare a working solution of volume, like say 10 ml from the 10 milligrams per ml BSA in various concentrations of 0.0 to 0.12 milligrams per ml. So what it means is that so we are going to prepare these concentrations from the 1% BSA or the 10 milligrams per ml BSA stock solution that we have. So we are preparing these various concentrations 0.0, 0.02, 0.04, 0.06, 0.08, 0.10 and 0.12 milligrams per ml in a final volume of 10 ml. So when we are done, we pick 1 ml of the prepared standard solution and subject it to the Folin Lowry method. So the next is, let us see the Folin reagent. So we said that like we have to do 1:3 dilution. So what it means is that if you pick 1 ml of the Folin reagent, we will have to dilute it with 3 ml of distilled water. So in this, so we can say, so we can pick 6 ml of the Folin reagent and dilute it with 18 ml, or 10 ml of the Folin and dilute it with 30 ml of distilled water. So if you look at this dilution, it is still in the ratio of 1:3. Now the alkaline solution or the alkaline reagent. So one key thing that we have to note is that so we are to prepare the alkaline solution on the day of use by mixing 50 ml of solution 1 and 1 ml of solution 2. So this is our solution 1 and this is our solution 2. So if you want to prepare the solution 1, so the solution 1 is alkaline sodium carbonate solutions, and to prepare this, you weigh 20 grams of sodium carbonate in 1 liter of 0.1 molar sodium hydroxide to prepare the solution 1. So for the solution 2, which is the copper sulfate sodium potassium tartrate solution, we weigh 5 grams of copper sulfate in 1 liter of 10 grams per liter of sodium potassium tartrate to prepare the solution 2. So now let's see how to do the 1% BSA dilution to prepare the working or the working concentration that we want to use to plot the calibration curve. So these are the working concentrations that we will use to prepare the calibration curve. We have 0.0, 0.2, 0.04, 0.06, 0.08, 0.10, and 0.12 milligrams per ml. And these are the now. So if we are to do a direct dilution, this will be the volume or the moles of the 1% BSA stock protein that we will need to prepare these various concentrations, and this is the volume of distilled water needed to prepare the final concentration. So for 0.0, we know that obviously it will be our blank, so we don't need any mils of the BSA, so it's just 10 mils of distilled water. So to prepare the 0.02 milligrams per mil, we need 0.02 mils of the 1% BSA or 10 milligrams per mil BSA and add 9.98 of distilled water. And to prepare the 0.042, we need 0.04 mils of the 1% BSA and add it to 9.96. So to prepare this concentration, we need this volume and add it to this volume of water. To prepare this concentration also, we need this volume and add it to this volume of water. And to prepare this concentration too, we need this volume of the 1% BSA and add this volume of water to it. And to prepare this concentration too, we need this volume of the 1% BSA and add 9.88 mils of the distilled water to it. And what we have to note is that the 0.02 mils is equivalent to 20 microliters. The 0.04 mil is equivalent to 40 microliters. And this is equivalent to 60 microliters. This is also equivalent to 80 microliters. This is equivalent to 100 microliters. And this is equivalent to 120 microliters. So this is just a table showing how to prepare the various concentrations over here from the 1% BSA using a direct dilution. So now let's look at the test protocol. So first, we are to prepare 7 test tubes containing 1 ml of the 0.00 to 0.12 milligrams mil per mil of the BSA from the 1% stock. And that was what I just explained from the table earlier. So when we are done, so we add 5 ml of the alkaline reagent and mix, and we leave it to stand for 10 minutes at room temperature. And what you have to note is that this results in the first reaction where the cupric ions react with the peptide bonds of the protein, which is the BSA here, to form a couples peptide bond complex. So when we are done with this, the next is to add 0.5 ml of the diluted Folin reagent and mix rapidly. And again, this is the second reaction in the Folin Lowry principle, where the couples peptide bond complex reacts with the Folin reagent to reduce the phosphomolybdic acid and the phosphotungstic acid to heteropolymolybdenum blue. So after that, we incubate at room temperature for 30 minutes and read absorbance at 750 nanometer. So after reading the absorbance, we plot the absorbance values of the BSA sample on the y-axis against their corresponding protein concentrations on the S-axis to generate a calibration curve. So after that, we determine the equation of the line. And I also advise that, like, for a detailed note or understanding of the calibration curve, you should also watch my video on calibration curve. Now, so let us look at the assumed results. So after preparing our known concentration and subjecting it to the Folin Lowry assay, so these are just the assumed, a table showing the assumed results. So obviously this is our blank. So for a concentration of 0.02, we have an absorbance of 0.024. For that of this, we have this absorbance. For that of this, we have this absorbance. For this, we have this absorbance. For this, we have this absorbance. And for this, we also have this absorbance. So to plot the calibration curve, we will plot the absorbance values against the known concentrations over here. So as you can see, this is the absorbance values on the y-axis, and this is the known concentrations in milligrams per mils on the s-axis. So we do this, and normally we use Excel to get our straight line over here, and to also generate the equation of the line. So from this experiment, we can see that, so this is the calibration curve with the equation of the line giving us y equals 1.0036 s plus 0.0022, where y happens to be the absorbance, the 1.0036 happens to be our slope, and the s happens to be the concentrations on the s-axis, and the 0.0022 happens to be our intercept, and this is our r square, which is 0.997033, to show that we did a good work.